In this video, we examine combinatorics, also known as counting. In this topic, we examine the four processes for counting. We'll consider when to use each type. We'll examine multiple examples of each, and we'll develop a process for classifying the situation in the problem that uses each of the types of counting processes. The first counting process that we examine is called the multiplication principle, sometimes known as the pigeonhole principle. It states that if a task A can be performed in M ways, so we count how many ways we can do the first task, and after we do the first task, a second task, we'll call task B, can be performed in N ways, then the number of ways to do task A followed by task B is M times N. An example will help us understand the application of this process. We illustrate the multiplication principle with this example. Suppose you want to count the number of different outfits that you can create from the 5 different shirts and 6 pairs of pants in your closet. And maybe you don't really care if everything matches, you just want a different look. There are 2 simple tasks that must be performed to create an outfit. First, you have to choose a shirt, and there are 5 choices for the different shirts. And then you have to choose a pair of pants, and there are 6 ways to do that. So using our multiplication principle, task A is the number of ways we can choose a shirt, so we note that each of the shirts can be matched with one of the 6 pairs of pants. So we have 5 different ways to choose a shirt, 5 different shirts. Then our task B doesn't depend on what we chose for the shirt. We have 6 choices for the pairs of pants, and the multiplication principle says that we should multiply 5 times 6, which gives 30, which is the total number of different outfits that are possible in this example. Now let's look at a second example where a manager of a baseball team having 14 players wants to choose the batting order for the first 4 batters. The first task, which is we'll call task 1, is to choose the leadoff batter. We will assume in the example that any of the 14 players would be a suitable leadoff batter, so there are 14 choices for the first batter. So we found in arranging this batting order, the manager has 14 choices for the leadoff batter. Once they've selected the leadoff batter, the question becomes, how many choices does the manager have for the person who will bat in second position? So we'll call that task 2. We've accomplished task 1. There are 14 ways to do that. Now we have to choose a batter for the second position, and there are 13 choices for the second position. And the reason there aren't 14 choices is according to the rules of baseball, a person cannot bat sequentially and follow themselves. In other words, the person who's batting first can't then come back to the plate and bat second. So for task 2, we have 13 choices, and continuing to choose the batter for the third position, there are 12 choices, and for the fourth batter, there are 11 choices. So by our multiplication principle, the number of choices that the manager has to arrange the first 4 batters, task 1, there are 14, task 2, there are 13, task 3, there are 12, and task 4, there are 11. The multiplication principle says that we should multiply these numbers, and we obtain the value 24,024. There are 24,024 different ways to arrange the first 4 batters when we have a 14-player roster. It may surprise you that there would be that many choices, but the issues that create that is that it matters what order they're in, and we've got a lot of choices of players for those positions. In this third example, where we will use the multiplication principle, several years ago, the state of Louisiana changed the structure of their automobile license plates to consist of 3 letters followed by 3 numbers. And the question we want to answer is how many different license plates may be possible using this structure. And so the simple tasks that make up this multiple task of creating a license plate are choose the letters, and we have three slots for letters, and then choose the numbers. So license plates are made up of 3 letters, then 3 numbers, and all of those choices must be made. Now, it's possible, and I'm not saying that this is the case, but there may be certain letters that are not allowed. For example, the letter O may be disallowed because of possible confusion with the number 0. Probably is not the case because the position of the license plates is that the letters are to the left and the numbers are to the right. Also, it could be that I is disallowed because maybe confusing I with a 1, and maybe Q is disallowed because of possible confusion with the letter O. We don't know that, but in the example, let's assume for the first part, let's assume that we can't use these 3 letters. Then in choosing our letters, and a license plate will have the structure that there are 3 letters followed by 3 digits. And it may be helpful to you when you're working with these multiplication type problems to just create a little set of slots where you're going to put the numbers of how many ways to do the tasks. So if we've disallowed 3 letters, then there are 23 remaining letters in the alphabet that could go in the first letter slot. Nothing in the problem says that a letter can't repeat, so we would also have 23 choices for the second slot, 23 choices for the third slot. And so we'd have that product, 23 times 23 times 23, being the number of different ways we could choose the 3 letters on the license plate. For the digits, we have a choice of digits from 0 to 9. There are 10 of those digits, so for each of the numbers, we have a choice of 10, 10, and 10. And that's assuming that no digit has been disallowed. So the total number of license plates with the 3 letters O, I, and Q not being permitted would be 23 times 23 times 23 times 10 times 10 times 10. And that product is 12,167,000. We continue this license plate example with the question, suppose that none of the letters or the numbers can be repeated and that there are no letters that are disallowed. And the question is, what does this do, or how does this impact the number of possible license plates? Now recall that our license plate structure has 3 letters followed by 3 digits. If we count the number of choices for the first letter with no restrictions, there are 26 letters that can be selected. For the second letter, since we are not going to repeat that first letter, that would leave us 25. And for the third letter, that would leave us 24 choices. When we select the numbers, there are 10 digits and 10 choices for the first digit. But since we're not going to allow repeating a choice of a digit, when we choose the second digit, we have 9 choices, and choosing the third digit, we have 8 choices. We multiply these numbers according to the multiplication principle, and we obtain 11,232,000 different license plates. These license plates would be described as they do not have any letters nor numbers that repeat. Continuing the example, suppose there are 168 different three-letter words that are not allowed because they're considered obscene. With this restriction, we want to count how many different license plates are possible. So the total number of three-letter combinations with no restrictions we find to be 26 times 26 times 26. We have a choice of 26 letters for each of the three-letter slots. That gives a total of 17,576 different three-letter combinations for the license plate if there are no restrictions. Those letter combinations would range from AAA to ZZZ with all of the combinations of letters between. Each of those three-letter combinations could then be paired with one of the 1,000 different three-number combinations, giving us a total number of license plates with no restrictions of 17,576,000. Each three-letter combination is paired with a combination of three numbers. There are 10 times 10 times 10 equals 1,000 three-number combinations. Those range from 000 through 999. And each three-letter word that is not allowed because it's considered obscene reduces the total number of license plates by 1,000. For example, maybe someone at the license office doesn't like the XXX letter combination, and that's disallowed. The 1,000 license plates with XXX000 to XXX999 would not be allowed. Each of the 168 three-letter disallowed words results in a loss of 1,000 license plates, giving a total reduction of 168,000 from the 17,576,000 total. We subtract and find there would remain 17,408,000 different license plates after these so-called obscene words have been disallowed. The previous license plate example used the multiplication principle for counting. The license plates allow repeated choices for letters and numbers unless stated otherwise. The multiplication principle for counting is the only counting method of the four that we consider that allows repeating a choice. So when deciding what process for counting to use, if repetition is allowed, the only choice that we have for counting is the multiplication principle. So let's consider another example. In this example, let's suppose that an internet website requires that you have a username and password, and that the password must have at least 8 characters in length, and each character must either be a letter or a number. The question is how many different passwords are possible. Now, in working this example, we're going to assume that all 8 characters in the password are used. Note that there are 26 letters and 10 digits, giving a total of 36 choices for each of the characters in the password. So with 8 characters in the password, we have to complete 8 choices. Each choice, we have 36 different items or choices for the first letter or digit and so forth through all of the 8 different parts of the password. Multiplication principle says that we would multiply these 36s, and that gives a total of 2,821,109,907,456, or about 2.8 trillion different passwords. Quite a large number. One might think, well, that's all we need. Computers are fast enough to where they could run through all of these possibilities rather quickly and guess a password if necessary. That's why passwords of late are more complex than these. In this example, we're going to take that password problem a little different direction. We're still going to require that the password have at least 8 characters, but we're going to put in a condition that the first 3 characters are letters that cannot be repeated. So instead of letters or numbers, the first 3 characters must be letters, and we can't repeat. So if we count those, the first choice would have 26. Since we can't repeat, we would have 25. And the third choice of a letter would leave us 24 letters from which we could choose. The next 2 positions must be numbers or digits, so I'll mark those as digits. And those cannot be repeated. There are 10 digits, so I have 10 choices for the first digit, but since I can't repeat, I have only 9 choices remaining. The last 3 positions can either be letters or numbers, but nothing that has been previously used. There remain 23 letters and 8 digits that have not been used. 23 and 8 would be 31. Nothing states that we can't repeat, so I would have a choice, or we would have a choice of 31, 31, and 31 for those last 3 choices. Multiplication principle would say that we should multiply these values, and so we multiply these values to obtain. This product gives 41,826,564,000 different password choices. And you might recall the previous example with no restrictions, we had well over 1 trillion, 2.8 trillion approximately. So when we put these restrictions, we begin to lose a large number of different passwords for the example. So to summarize this first counting process, the multiplication principle, the multiplication principle is the only counting process that allows us to repeat a choice or repeat a task. The first part of the password example allowed us to repeat a choice of a letter or number. We count the simple tasks that make up the larger tasks and multiply the number of ways to accomplish each simple task to obtain the total number of ways to perform the larger task. That is to say, if task A can be performed in M ways, and after we've done that, a second task, task B, can be performed in N ways, then the number of ways to do task A followed by task B is M times N.